Hi, this is Coach Dorf again. We're looking at the solutions to some of the related rate problems from section 3.9. Here's problem number 15. A street light is mounted on top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? So the first thing I would do on this one is draw a diagram, because I think it will help me understand what I need. So say here's the pole with the light there. So we know that this is 15 feet. And we say here's the man. And we know that he's 6 feet. The tip of his shadow here is at this point. And we also have that the man walks away from the pole at 5 feet per second. So we're going to need this distance here, the distance from the pole to the man. We're going to call that x. But we're also going to need this distance here, y. So that gives us x and y there, and the numbers 15 and 6. And I'm just going to draw another triangle to make it a little bit clearer. This is 6, this is 15, here's x, here's y, and this whole thing here is x plus y. All right, with this, what are we given? Well, we're given that man's walking away from the pole 5 feet per second. So we know dx dt is 5 feet a second. And we're supposed to find how fast the tip of his shadow is moving. Now, what's the tip of the shadow? Well, you might think it's just y, but actually it's x plus y, because it's the distance from the pole to the tip that we're interested in. So it's going to be d dt of x plus y. So, and that's going to be, again, how fast the tip of his shadow is moving away from the pole. So you're supposed to find that when he is 40 feet from the pole. So when x is 40 feet. So that's what we need to find. Now, we want to find a relationship between x and y here, and that will simplify the problem. So we want to find an equation connecting x, y, and given numbers. And to do this, we're going to use similar triangles. Now, it may be a while since you reviewed similar triangles, so let me show you what I mean by those. Similar triangles are triangles that look like the same shape, but one's bigger than the other. So in this case, a big triangle, it has a height of 15 and a base of x plus y. Inside it, to the right, is a smaller triangle that has a height 6 and a base of y. These two triangles are similar. And what's nice about similar triangles is there is a connection between the lengths of the sides, or the ratio of the sides. So if I use the smaller triangle, if I take the base over the height, that's going to equal the base over the height of the larger triangle. And that's always true for similar triangles. So then I can use that equation, and by cross multiplying, I get 15y equals 6x plus 6. If I bring the 6y to the other side, that's going to give me 9y equals 6x. Solving for y, I get equals 6/9 x, or y equals 2/3 x. So that's going to be a useful quantity to help me in solving this problem. All right, so now we want to find d dt of x plus y, how fast the tip of the shadow moves. That's how fast tip of the shadow. All right, so I've got d dt of x plus y. Well, I'm going to use now the fact that y is 2/3 x to get d dt of x plus 2/3 x. So that's a d dt of x plus 2/3 x is going to give me 5/3 x. And when I take that derivative, I get 5/3 dx dt. Notice that I got a value for dx dt in the original problem. And it makes sense that I don't want to keep the y in there because I don't have a value for dy dt. So it makes sense that I need to get rid of the y and express it in terms of x so that I can use just dx dt, since that's what's given to me. All right, so at this point then, all I need to do is substitute in the value of dx dt, and that value we were given is 5 feet per second. And so I get 25/3. And what's my units? Well, 5/3 is just a number. The 5 was feet per second. So when I multiply this together, I just get 5 feet per second, and that's my answer. Hopefully that helps.